Yeah, okay, okay, very sorry. Hmm. So just follow this one, follow your thoughts. Uh, so this one as the degree of, so this unavailability of thermodynamic potential or thermal energy for conversion into mechanical work, so many words there. In physics, interpreted as the degree of disorder or randomness in the system. Okay, yeah, this is related to physics. Okay, the disorder or randomness in the system. Okay, interpreted as the disorder. Let's say, now this is quite easy to imagine. Okay, this is quite easy to imagine. Let's say like this. Uh, and will let me underline this first. Okay, think about this till I put a figure here, interpreted as the degree of disorder or randomness in the system. Okay, I hope you can see that slide. Well, yes. See this picture. So you can see molecules. Okay, those are the gas molecules. The molecular movements are quite random. Okay, the more random, the disorderness is quite high. You can see the if this needs to do some work, maybe let's say if this pushes this way, let's say example, if a work should be done on this way, okay, but some molecules may be moving on the other way. Okay, some molecules, some may be moving on this way, some may be moving on the another directions, but resultant somehow, if this is the loosened surface or a piston to move here this area of surface, somehow because of this collision of molecules, because of this loosened surface, this may move. But this is the kind of randomness and this disorder you are seeing in converting thermal energy into mechanical energy. When thermal energy is there, molecules are really active. Molecules are really active. But even the molecules are active. If the disorderness is there, if the disorderness is there, so you won't get the 100% potential as the mechanical work. That is not possible. Okay, so this is one of the examples. Okay, yeah, degree of disorder or randomness in the system. So this may be one of the reasons you can consider this as the randomness or the disorder. Normally for the gas power cycles, vapor power cycles, you may see this. Okay, think about this till I put one more. picture there. So if we put this kind of picture here, this is a piston cylinder. So you can see in this mechanism or in this arrangement, the piston moves. Once the piston moves, it's doing a mechanical work. It is very quite obvious that here the thermal energy converts into mechanical work. Yeah, thermal energy convert into mechanical work. But even here, with the combustion, of course, the molecules are energized because of the heat generated. But still here, when the piston moves down, so the system means here the enclosure moves down, yeah, molecules somehow, how to say, the more energized molecules, of course, moves down, because when the piston moves down, molecules expand towards this, moves towards this. The reason is the molecules more violent, and this pushes this piston down. Pushes, because this is the only surface vulnerable to move. This is the only surface possible to move, the piston, the surface here. So because of the violence, so the piston moves. When the piston moves, there is a tendency of more molecules moves towards this. Yeah, more molecules move towards this. Because wind moves, if not molecule move, a vacuum created. Since there is no possibility for vacuum, molecules move together with the piston. So that is what we call the expansion of this energized or combusted the gas, okay, or the air fuel combusted uh, high temperature energized gas makes the piston down, and together the molecules also as a bulk would move down. But still, the disorderness is there to the fullest. Disorderness, because some molecules may move in the direction of the piston movement. True. Some molecules may move in the direction of the piston movement. But there may be some molecules, yeah, even moving in the reverse direction. That's possible because of the randomness. Because of the randomness. That's why. So for this kind of things, I think that mainly what the generation gathered experience matter. That's why. So this kind of things, the modeling of the turbulence inside this combustion chambers or in the piston cylinder enclosures, even though you do modeling or whatever, you cannot, you can understand the reality only up to 70% maybe. Yeah. Only up to 70%. Majority moves, but some molecules move this way. Okay, you should understand this. You should understand this. Okay, that's why. So there is a theorem. Anyway, there is a theorem. It says just because of this. Let me group this. This goes together with this. So now this entropy, unavailability of thermodynamic potential or thermal energy for mechanical work. I hope you have some understanding. So anyway, to keep the memory, so I keep the things over here. Okay. Now imagine, it is truly obvious that not all the molecules are contributing to do this work. Not all the molecules are contributing to do this work. Not all. Okay. So you can see the talk here. So there's some work done is there, but not all the molecules are contributing. Okay. So finally the piston moves here and you can see the torque here. Because of this connecting rod and the crankshaft, the arrangement connected with the piston, this mechanism makes once the piston moves down, the shaft turns. Okay, the flywheels and all are connected to the shaft. Okay, don't worry. So this is the obvious thing. Okay, that's why you need. This is the real thermodynamics you are learning. That's why the entropy knowledge is very important. There is a statement called Kelvin Planck. Okay, Kelvin Planck. Kelvin statement. Okay, yeah. So you have to understand this. Yeah. So anyone can understand this. There is a statement. Mentioning this fact that not all the thermal energy is converted. It is not possible to convert all the thermal energy into mechanical. It's not possible. Yeah. So that is what the statements say, mainly because of this molecular disorders. Yeah. That's why if you are smart enough, if you are wise enough, you can minimize this disorders. That's what you can do, but you cannot eliminate the disorders. Okay. So in the Kelvin Planck statement, this says, of course, here the engine. Let me do the engine as this is operating a cycle. Okay, this is operating a cycle. So this is, let's see, engine. I hope you can see it. I hope you can see it. Still, I couldn't repair my notebook. Engine. Fine. So this receives energy. Okay. This receives energy. So what energy this receives? Thermal energy. You see here thermal energy. This receives thermal energy. Okay. This receives thermal energy. Let's say this thermal energy received by the engine, of course, by the system here, by means of combustion of fuel. Okay, this receives thermal energy. Okay, by means of combustion of fuel. obviously, combustion of fuel. And this delivers some work. Delivers some work. Same like this. Okay. So receiving thermal energy here is in a way of combustion. In a way of combustion. Okay. So in a way of combustion, so let me put some indication here. In a way of combustion. Okay. Yeah. This receives thermal energy. Combustion. So you need quite common sense, okay, in a way of combustion. So combustion makes thermal energy available to do work. But what happens is not all does work. So what happens? This molecule is moving opposite. Those will be the losses. Those will be the losses. So let me mark the losses here. Okay, so you have the thermal energy in, thermal energy loss. Okay, and there is a net, of course, in minus loss is the work done W, that is the energy, the conservation principle. Okay, so what Kelvin Planck statement said is, okay, not all the thermal energy available for a system does convert into mechanical work. Okay, yeah. So that is what the Kelvin Planck statement said. This is because of this molecular disorders. This molecular disorders is the system's thermal energy is unavailability. There is a portion of thermal energy unavailable for conversion into mechanical work. Even though thermal energy is there, the thermal energy means the molecular motion, the violent nature, the energized molecule. Yeah, it reflects the temperature as well, higher temperature. Yeah. So not all the energy available transferred into mechanical work. So that is what the Kelvin Planck statement said. Okay. So let me duplicate the slide. Yeah. Actually, we are learning something very good there. Yeah. So the Kelvin Planck statement said, not all the energy, okay, all the thermal energy some issues here. Not all the thermal energy energy converts or transformed, okay? Let's say converts fully into mechanical work or simply work. Okay. This is the statement. Actually, the real statement starts with the wordings. It's a serious wording. It is not possible. That's how it starts. See, it is not possible. It is not possible to convert, okay, to convert all the thermal energy available into mechanical work. Okay, so that is how it's properly defined. It is impossible. That's how it starts. It's impossible to convert all the thermal, okay, all the thermal energy available into mechanical work. It is something like this. You have the thermal energy, you convert all into this. This is not possible. Okay, this is not possible. Okay, so here if we think Q in, Q means energy in, thermal energy in, let's say thermal energy as Q. Okay, Q in, Q in, and here you have W out, work out from this engine or the thermodynamic system. So what this says is Q in equals W out is not possible. Okay, that is what it says. Is not possible. Okay, is not possible. Is not possible. Okay, it's not possible. It's not possible. That's how it says. Okay. Then what is the possibility? Okay, so this is the Kelvin Planck statement. So inside you will see the entropy, because now you know what entropy means in physics. So this is something like a second law in thermodynamics. You can explore this statement, second law, but to understand this, you have to listen for this kind of knowledge sharing. Otherwise, it is just a memory only. Okay, so it is not possible. So what is the possibility then? What's the possibility? What's the possibility? You have to have, this is the possibility. So there is a loss. Okay, there is a loss. This is the possibility. So you have W out here. So Q in is here. So here Q loss. Even sometimes W loss also there. So those are the practical aspects, but even the theoretical point of view. So this is the situation. So Q in equals W out is not possible. Okay, is not possible. So then what is the possibility? It is not possible. It's not possible. So now I'm writing the possibility. Q in is W out plus what? Q loss. This is possible. Okay, this is Q loss. Q loss. This is possible. Is the possibility. Is the possibility. Okay, I hope you can understand this. Yes, so this is this is not possible. So this is the possibility then. Okay, so this is the possibility. So Q losses here. Okay, W out is here. So this is what here the Q loss is 0. Q in equals W out, which means in other words, Q loss. equals 0, which means Q in equals W out. Okay, Q in equals W out. Because when Q loss is 0, Q in is W out. Is not possible because of this disorderness or randomness. This is the reason. Because of this. I hope you can understand very well. Okay. So this is the modeling of an engine. Yeah. That's why you can see that if you are exempted from the thermodynamics, you will surely lose this knowledge. Okay, so that's very important to join this class. So let me duplicate this slide. So that's why. So when it is not possible, always there is a term efficiency. Okay, always there should be a term efficiency because of this issue. So there should be a term called efficiency. So neta is the notation generally we use for efficiency. This is the word. So neta is here when Q loss is 0, neta is 100%, but no 100% efficiency is there. So what is neta? Now we can define it. Efficiency. So I have to get some space here. So I put one definition. This is the situation. This is the situation. So you have the efficiency term there. This is the possibility. Is the possibility. Then you have the term efficiency against what? Desired output. To our intention is to get some work done. Okay. W out divided by the energy in. Okay. Divided by energy in is Q in. So this is the efficiency. Very interesting. Okay. So this is what we call the efficiency. Efficiency. Okay. I believe this spelling should be okay. Yeah. So this is how you model the thermodynamic system. And to have a better understanding of this, you should have the understanding of this entropy. Okay. So this is the situation. Okay. This is the situation. So you can see, yeah, this is somehow based on the entropy definition, we came to the engine side. And if you go to your last week evaluations, you may see the same. You may see the same. See, the higher the temperature, this is your energy input delta Q to the system. Maybe something like an engine. Yeah. Your loss of availability is delta S. Okay. Loss of availability of thermal energy for mechanical work. Loss of availability means unavailability. Say, you can see the unavailability reduces with the higher temperature. Oh, loss of availability is reduced. Also, the availability is increasing when loss of availability is reducing. Okay, see, unavailability is increasing, which means when your heat transfer is taken place at higher temperatures, even at 427, you may be able to run an engine. Okay, you may be able to run an engine at 427 high temperature. Of course, even in minus 23, you may be using refrigerant like the low temperature vapor. Yeah, but your loss of availability is very high. See, 36. Here is 12.85. So that is the point you should understand. So this is totally, you know that high temperature energy is very, very useful for converting that thermal energy into mechanical work. So which means there is a high thermodynamic uh, potential for mechanical work. Okay, high thermodynamic potential. So this is the same. So this just an application. So I put some boundary node through insulation. It's the same. Higher temperatures, loss of unavailability is less. So this one is same. Outside temperature there is yeah. So you have the somehow the same heat transfer to inside. So when you have the beta insulation, maybe this one. Yeah. So you can see with the insulation beta insulation, even though inside is very low and outside is constant, you can see the heat transfer to inside is less. Yes. Sorry, here the internal temperature increase, okay? So when the internal temperature is rising, heat transfer is less. So then, see the less heat transfer also is very useful, means the receiving of unavailability of uh, mechanical energy from the receiving of heat is lesser. So this is based on the high temperature here, outside is the same. So receiving less energy. So when you receive less energy to the system, then that also contributes for less increase of entropy, means the unavailability of thermal energy to work for the conversion into work is less. Unavailability is reduced. You have to understand this. Then again, this one same temperature inside minus 23. So here you can see you are improving the insulation C. Insulation C improving, heat transfer drops. That's why. So again, the entropy increases less. So lesser the entropy increase, the better the solution. Okay, the better the solution, the better the thermodynamic system. Okay, that's why yesterday, based on the analysis, I brought this from the physics definition. It is quite acceptable when we move towards the engine's power, you will understand this much better. And finally, we managed to model the heat engine. Okay, heat engine model. We managed to model it. Yeah. So now it's a step-by-step knowledge. So nothing to memorize, also nothing to forget. So all based on the practicality. That's why the entropy is quite practical. Even though they are theoretical calculations, it is quite practical. Okay. Further continuing this, yeah, you all look silent. I just want to check whether you can listen to me or not. Yeah. Do you hear the lessons well?
Yes, sir, we are here.
Okay. Very good. So here the issue is mainly because of the entropy. So you know that that's why. So when we talk about the technology, the Japanese and Chinese, this entropy minimization is something like quite challenging, and it is not to say secret, but some hidden knowledge that no information, no tangible or no effective informations can be seen in the books. Yeah, the engine, maybe the housing design and the surface treatments, the finishing and all, the tools they are using, surface treatments, operating temperature, so many parameters there. So generation to generation, this experience knowledge, that is what the Toyota engines got lesser entropy. And you can see their technology also improving a lot in the sense of combustion. Combustion control, now they have all the electronic solutions and all. And then other than the combustion, when it comes to the functionality of the engine as to produce mechanical energy, they are also the engine designs, manufacturing, fabrications, more component developments, all are very nicely optimized, and those are, I would say, world class. That's all. Even Germans, they are doing engines. Europeans, of course, including Germans, Americans, all are doing engines. But when it comes to the energy saving, reliable engines, when it comes to technology, I believe Japanese are better. The reason is their culture. The reason is their culture. So their culture and their practices in the industries. That's how. So all the young recruits to these companies, they were trained under very senior, experienced people, and slowly these young chaps, technologists and engineers, while they are receiving knowledge from the seniors, they are improving their positions and the knowledge and their pay, salaries and all, and they are moving higher and higher with their experiences, and finally they will be on top. So this culture is there in very good R&D based companies. So Toyota is one of the best companies with R&D culture. So you can see the way they are doing. Same other Japanese car makers also. Not only the car, the other solution providers, they are better. They are better. So even when it comes to aircraft industries, the engine. So those turbines in Boeings nowadays, I can go on, I can go on Dreamliner, they claim that their their planes are very much energy efficient. See, why now only energy efficient? Why not earlier? It is like that because because improving the engines, efficiencies, and minimizing the entropies. Those are something not that fast you can do to the fullest. Those takes time. So today those Dreamliner engines are better, but in future there will be better and better engines or the turbines. That's how it is. Even in the rocket engines, it's very famous that Russian rocket engines are less costly and more fuel efficient than US rocket engines. See how the Russians perform better in that space technologies? Because those are not in the books and those are not based on the simulations. The simulations, the digital simulations, programming and all, those things are in their mind. So they can visualize, oh, somehow this technology genius people, they bring the changes to the technology. Same way, the gear trains, the gear systems. You know the gear systems full of lubricants and all because the frictions. The friction is the disorderness. Yeah, it really, friction really losses energy. And the lubricants are there to control the temperature rise and all. So the energy efficient transmission systems, gear transmission systems, very important, but not all the plane makers, car makers have those. Not all, but a few they have the technology that is unexplainable to the others. If that can be explainable, everybody can do the same. But it is not possible. Same like Jinadasi's Talaguli තියෙන තවත් තලගුලි තියෙනවා. But Jinadasa's Talaguli is still considered better. Somehow the uniqueness you see there, yeah, compared to the others, so they cannot make it. They cannot copy the recipes, the secret recipes there. Same way, the secret knowledge, undocumented, unexplainable, untraceable, but the knowledge is there. That knowledge is very important. Even even for the governance of the country. So Ratwa Rajyapalaneta. So we have to have that kind of knowledge passing from the generations. That is very important. The good practices and all. That's why.
This extreme pain as
Oh, sorry, Buddha. Sorry. Yeah, let me. Thanks for reminding. Thanks for reminding. Yeah. Good.
okay,
That,
sir.
yeah, no, okay. So that's how the knowledge is important. Knowledge, the experience knowledge is very important. That only can make the changes, make the improvements. The experience knowledge. So I put here maybe the experience knowledge. Experience knowledge. So that's why experience knowledge. This is very important. This is not the book knowledge. Who can remember the books? Yeah, that is not possible. Yeah, experience knowledge. This is extremely important. That's why, so you are lucky if your workplace you have seniors with experience and very good qualities. Then you are lucky. That's why. So somehow, if you are not receiving that experience knowledge from the seniors, you have no choice. You should be wise enough. You should have this knowledge somehow with the interactions of others. And one day you should be somebody to share your knowledge with the society. Yeah. So that's why never undermine the seniors in your organizations, because some they have the hidden the knowledge, they are not showing it, they are not sharing, but they are performing somehow. Sometimes you see those as little smart, some little things, but those are really matters. That's why. So try to associate with senior experience people, no matter low level. Yeah, because when it comes to experience, there is no much different as high and low. Even sometimes the low level technicians, the senior ones, and even the younger ones, they have knowledge, because the real thermodynamics is not in the books, it's not the equations, it is their real. That's why. So you should be smart enough to interact with the organizational expertise you are seeing from top to bottom, irrespective of the positions. Yeah. Yeah, even when I work in companies, of course, in overseas good companies also, I'm very good from top to bottom. Yeah, top to bottom, all are very good with me. So even I'm receiving the knowledge, even they are receiving the knowledge. Yeah. One time I got one senior engineer, he was in his 70s. He's a Chinese guy. He's a very experienced guy. So his knowledge is truly good. But he's an old Chinese guy born in China. But this guy, he cannot explain it, but the knowledge is there. So those days, I call him general because he's senior to me and he's a veteran. He called me professor because when it comes to analysis, no one can match me. So whatever he cannot solve, I can solve. Whatever I cannot solve because some experience based, he does it. So that's why we have a very good knowledge sharing and partnership. So those really helps. Yeah, that's why very important to work with seniors, no matter under you. Yeah. So that's why I mentioned my experience. Sometimes the young guys. Yeah. So you should be smart to have a very good team from the young to the seniors and to share the knowledge, receive the knowledge, and get the things done. And everything should be knowledge based. Then the innovations and all the things can come. Yeah. So everything practical, everything should be finally out of the books, should be in the field, should be in the nature, should be in the things what you are doing. Yeah, that is very important. So that's why. So I'm underlining this important of the book knowledge, but you should go beyond the books. Yeah. So experience knowledge. Yeah. So that is very important. So this Kelvin plan, that is fine. So then the other this disorders, naturally they are in the gas and liquid. Yeah. Even in some solids, you can see the disorders in the system. So disorders. Also, sometimes the friction, friction also makes losing of energy. Yeah, it friction makes the uh, increasing of unavailability of thermal energy into mechanical energy conversion. Friction is one of the how to say one of the key concerns. Frictions. Yeah. Frictions, especially for the engines and all, for the gearboxes, even liquid friction and all. The friction, the lubrication is there because of the friction and all. But perfect lubrication solutions are no more there, not there. People are still doing R&D and all. So you can see lubricant has become a big business. The issue is the friction, but friction is important because without having friction, it's not possible to exist here. Yeah. because you have no control. You have to apply the brakes or slow down, change the motions and all. Somehow friction is very useful. But some cases, the same strength, the same use becomes the disadvantage. That's all. So friction is another contributing factor for entropy. This can be the fluid friction, the friction between the solid surfaces. Yeah, friction between fluid, it's relating to the viscosity and all. Yeah, so this is very important. Yeah, so how to manage friction? Yeah, so managing friction, this managing the randomness, the disorderness, those are very important. And also, sometimes disorders can be more, let's say, example, high-speed engines. High-speed engines and the low-speed engines. Low-speed engines may be more energy efficient. Example, when the energy is efficient, engines are running slow. It's example, on the top gears, engine speed is, let's say, 1005, but on the low gears, engines running at high speeds. The high frictions may be there somehow, you can see. The low speeds and the less friction all matters. Yeah. So you can think how to improve how to improve the minimizing of entropy. Friction is one more thing. And we have some more. So let me put it here. These all are experience based. That's why I can share with you. Temperature difference, delta T. Yeah. Temperature difference is the other concerns. Let's say uh, in many applications, if you design, let's say, of course, so many applications in the boiler designs, in the design of heat exchangers, let's say, here in the wordings, designs, designs, boilers, design of boilers, heat exchangers, heat exchangers, exchangers, heat exchangers, even, of course, your design of even the kitchen appliances. We have a lot of like a kettle design, let's say kettles, appliances, let's say including refrigerators and appliances. Even the, the, the heat increase in the sometimes unnecessary heat generation. Okay, heat generation in electronics, electrical, electronics, electronics, or electronic components. So you can see this kind of so many things, even your the computer processors, Yeah, you need cooling, microprocessors, even your telephone, your mobiles. You have the heat generation in electrical and electronic and mobile. So the, let's say, the communication, devices and components. So you need cooling there. Okay, devices and components. You need cooling. Refrigerators. So many things. So those are very important. So when you are designing something, example household, whatever, or in industry, whatever, this consideration of delta T is very important. Some may feel that high delta T is more compact, but the lower delta T is very important for the efficiencies. So delta T. So the less friction, less delta T, we call it's kind of a no friction, and the minimal delta T, we call this. Sometimes we use the word reversibility. Sometimes we use the word disorders. Okay, so these are the things: friction, the temperature difference. Delta T means temperature difference. Temperature differences. Temperature differences. So these are very important. Yeah, these are very important. Yeah, these are very important. So, very good. This one. So let me read this. So I take some out here. I just keep the figures on. Yes. Yes. Very important. Put into the picture form so that it's easy. Efficiency. Also here. Good. So the frictions, temperature differences. So friction increases the temperatures, the disorders, the randomness, and all. Even the temperatures, it's the same. It's the same. Higher delta T means you will see somehow the flowing of heat at higher higher rates. So higher rates means you are pumping heat at higher rates to some place, means there the disorders will be more than receiving the heat slowly. See, heat receiving, slow heat receiving. Yeah, even slow heat releasing, slow heat receiving. So it's very quite practical. Okay? Quite practical. So what else? There can be more. There can be many more. You have to think. Okay. And the other keyword for this, let me write. Let me type it here. The word reversibility. Reversible. Reversible. Word reversible. That is very important word. Okay. The degree of reversibility. More reversible means quite less entropy. Actually, reversible in the sense zero entropy increase. Okay. Reversible means how to say uh, not to say zero entropy, but the irreversibility is less. Okay. If the fully reversible means it is really with some good uh, orderness and no randomness. Okay. Yeah. So disorder means is the no order there means more random. Okay. Direction. So the reversible is the word. This is important. And this is about the order. Yes. Reversible. Reversible. Means, well ordered. Okay. Ordered. Very nice. So you can put the word well here. Well ordered. Well ordered. That is reversible. Okay. Irreversible means then, you know, opposite of reversible. Yeah, let me make it big. Okay. So the opposite of this is irreversible. Irreversible. So you have to add irreversible means disordered. Disordered means random. Okay, random. What? Mainly the molecular movements. Molecular movements. Okay, very good. So we will go for some more samples. So in semiconductor devices, let's say components. I'm not that familiar. You know better than me. Those are some diodes, transistors. Nowadays, even maybe the capacitors. I don't. Okay. These components are well ordered. Okay. The raw material is SiO2, if I'm not mistaken, silicon dioxide, or we call this silica. Silica. Okay, not silicon, eh? Yeah. Silica. So the silica. So those are silicon based semiconductor components. So here in the process, so to produce what they are producing now, produce now they are producing, of course, TV screens, and even the mobile, the phone we call the displays, TV and mobile phone displays. Mobile phone displays. Display. It's a very high-tech industry. So those are really the diodes, LED nowadays. Earlier the LCD, liquid crystal display, now light emitting diodes. They call it TFT, thin film transistor LED, if I'm not mistaken. Anyway, here what they are doing is, of course, there are so many. Even now you have the LED bulbs and all, the LED for lighting and all. So all the semiconductor, okay, LED lightings, solar panels, even the thermal junctions like the Peltier devices. Yeah, the light, LED, lighting diodes. Then the Peltier means the thermal junctions, Peltier devices. Those are the basics. Basics. So you are combining all and you do the components maybe, etc. So those are well ordered. Okay, well ordered. Even the electromagnetic components to develop the or to manufacture the magnetic components and all. So those are well ordered. Well ordered means low entropy. Okay, well ordered. Well ordered. That's why you can see in the LED light energy consumption is very less, which means low entropy. Low entropy means well ordered. To understand? Yeah, we can say simply we can say less energy consuming, less heat dissipating, well ordered, low entropy. Low entropy products. Okay, low entropy products. But you believe it, producing this, okay, producing this manufacturing process is the other way, high energy consuming process. This consumes a lot of energy, chemicals, hundreds of chemicals and products well ordered. Okay, products well ordered. That's why energy saving, low energy consuming, not like the last time the television, this big cathode ray devices, no such things. Here, it's very thin, flat, less energy consuming, less heat dissipating. So the product well ordered, low entry, but manufacturing process, the other way, is high entropy process. Manufacturing process is high entropy, but the product is low entropy. But it's okay to go high entropy because these products may save the energy globally and may provide some better solutions. So the process high entropy, that's why you cannot have semiconductor industries everywhere. Only the countries with very good energy infrastructure like nuclear power plants. Korea, they are very good in making the devices, mobile devices, TVs, laptops and all. Taiwan here, Japan here, China. So they have this high-tech industries, high entropy industries. And their products are low entropy with nanotechnologies. Yeah. So high entropy industries, low entropy products. Yeah. Even Germany, they have the nuclear, they develop this kind of electronics, electromagnetic devices. So you can see in Germany, France, they are doing. So Italy, they produce, US. So you can see all these high-tech industries, high entropy, no matter they need high amount of energies and they have nuclear power plants everywhere. But India, they have the nuclear power plants, but they don't have high-tech industries. The reason is maybe they are using that energy mainly for the, of course, to support 1 billion population. So they are not that exporting same like China. So they are mainly for the basic power needs, transportation, some basic industries, all, but not for high-tech industries. Somehow high-tech industries like semiconductors not there. So that's how. So these are the entropy, the experience knowledge. So you should know this. So our industries, okay, semiconductor component, this is an industry, very nice. This is an industry. We have the industries. What are industries we have? We also have industries. So when you think of the industry, it is very important to consider whether this is high entropy industry or low entropy industry. High entropy processes, low entropy processes. Of course, metal industry is high entropy. It consumes a lot of energy. But finally, it produces low entropy products. Yeah, that's true. So that is about the entropy. We can talk a lot. So one more about the second law. Yeah, one more about the second law. Call it Clausius inequality. I think I mentioned it earlier. Clausius inequality, if I'm not mistaken, I have shared it somewhere, if I'm not mistaken, somewhere in the slides. I use the word? Yeah. You can see here delta is greater than or equals delta Q by T. That is the process inequality. Yeah, here you can see this is a process inequality. We have to discuss this as well. Somehow for the, I think we have discussed this. Because the equality when the things are reversible totally, if not delta S is greater than delta Q by T. That's why even in the reversible processes, there are increasing of entropy because it's like that. Okay, any
Sir,
more
excuse
question?
me.
Yeah, Bhuta. Yeah,
Sir, excuse me.
yeah,
Peltier module, Peltier devices means?
Peltier, those are the thermal junctions. Say again, the semiconductor devices. You can browse the web. Peltier technologies they are using for cooling solutions.
Yeah,
Peltier.
sir, is it a efficient way?
No, not efficient. Not efficient. Yeah. But for some applications in the compact places, limited spaces, so still people are using it. Example, like in cars, if you need a cool box, you cannot have the normal compressor system. You are using the Peltier. Not efficient, but and also not for deep cooling. This is for some simple cooling on the road, maybe. Oh, that kind of applications. Yeah. Less efficient applications, but that may be the best solution for that. Yeah, it depends on the situations. Peltier solutions. Yeah. I think COP, the efficiency is only about zero point 0.4 something, even at the little high temperatures. That's why. So the COP of normal vapor compression is 1 plus, but this is less than 1, maybe around zero point 0.4 if I'm not mistaken. Yeah. Good, Vitala. So this is about entropy. And I have some more here. So today I'm going, actually after discussing the entropy. So, okay. And also one more thing. So how you are going to minimize the entropies in some processes, your designs. So that is what you should aware. So whenever you do a design, so try to do low entropy solution, minimum entropy as possible. That is very important. So that is how you should be smarter in doing the designs. Yeah. The minimum entropy. Temperature differences quite less. If you have some friction issues, you have to focus on that as well. Yeah. Likewise, even the speed wise, you can go for not for the high speeds, also not for the slow one, the moderate ones. Even the heating, slow heating is it's a rate, heating rate, heating speed. So when you heat it slow, you are really transferring less reversibility. So even when you design a kettle or a boiler, so the less irreversibility is better. Because if you design a boiler with very high power burner and all, finally what will happen? Your steam generation is not there because of you have the formation of the vapor barrier underneath the surface. So finally your tubes will be melt. That's why. So same way, the slow boiling also you have issues because the heat process and also optimal solutions. It is very important. Not to say very fast boiling, slow boiling. Even when you buy a jug kettle, you see the wattage, 1000 watt you have, 750 watt you have, maybe same 1 liter. That is important, the rate. So 1 liter, 1000 watt heater with jug kettle and 1 liter with 750 watt jug kettle. Actually, I would go for 750. The reason is slow boiling. It takes time. But even you can put some herbs there. Yeah, it slowly boils. Yeah. And that is low entropy, what you call less noise, more efficient somehow. Even when you select an iron, so you have all the features, but if you can go for some less capacity, the less wattage with the same size, same application, it's a good choice. It's a good choice. Your ironing speed, the heating may be slow. Slow is better. Sometimes the fast heating, even your clothes can get burned. You know, the entropy levels are so high that you cannot control it. You are too late. Yeah. So that kind of that's very interesting. Yeah. So in the day-to-day decision making, even a cooker, when you buy a gas cooker, it, for your application you should get the right one, not the cookers with the big flames. Maybe it's for your application. Even when you take the rice cookers, if you need to cook maybe half a kilo, or if you buy maybe 1 kilo cooker to cook half kilo, it's really unnecessary entropy generations. That's all. So it is not about the energy losing, that is one more thing, but the entropy losing is another. So if you need to have a small cooker, rice cooker, better the low wattage ones. Slow cooking, slow heating, and the long lasting. Yeah, that's why. So that is one of the decision makers. Those who knows thermodynamics and the entropy very well, they will go for that kind of options. Yeah. But some maybe, oh, this one is very high power and maybe very good. They buy it for fast. But fast means it is a kind of slowness again, you know. Fast is slow in terms of reversibility, in terms of uh, entropy reduction. Fast means actually slow. Slow means in terms of entropy, it is fast. So interesting, this entropy concept. So even a pedestal fan, if you are buying, maybe of course the two pole is very fast, maybe 3,600 RPM, but four pole motor 1,500. It is bit expensive. The slow speed 1,005 speed fan is expensive, and the two pole 3,600. The high speed fans may be quite cheaper. But you see the technology, the difference. Again, you can think of the entropy there. Slow, yeah, but of course, slow, but you will get the sufficient one. Yeah, so that is quite interesting. So interesting designs. So whatever your designs, energy solutions, maybe when you are installing solar panels or a windmill, whatever. So you're buying an appliance. So these are the things you can consider. Even noise. Noise also related to entropy, you know, unnecessary noise, vibrations, high friction. That's right. Noise also is part of entropy generation. Noise and vibration. So very interesting this entropy point of view. And as the technologist, if your knowledge on entropy is not there, I mean the sense of knowledge, not to say the memory, but the sense of entropy knowledge, the sense of entropy is not there, it is something a huge shortcoming. I would say it's a huge shortcoming. Yeah. So you are looking for equations, but you do not look for your inborn technology talents, because entropy you need to get something within you. That's all. So very interesting, because technology is everywhere, but not all are expressed in words and equations. Yeah. So that's the point. That's the point. Very interesting. So even in air conditioning solutions, or heating, cooling solutions, refrigeration, whatever solutions, or the entropy consideration, slow rate or moderate rates, that is very important. So you can see for the moderates, your pricing may be a little bit high, but your returns may be there. It may be safer even to use. Very interesting to find this one. So I think this is wonderful. Today discussion. And today I thought of discussing a little more about the steam tables and also about the steam properties. But today it seems no time for this to discuss, especially this kind of plots. Those are also laboratory, based on the laboratory tests and all these charts. Even in Coolpack, you can see this kind of charts. So I want to check your the sense of acceptance of this kind of charts. Yeah, not the memorizing, but justification. Yeah, is this justified? That is very important. Maybe next week I will look into this one, but still I have to remind you. I asked you to do a tutorial, so you have to do it. You have to do it. You have to pass it to me. You have to do it and pass it to me. The tutorial or something there. About the two-phase steam, if I'm not mistaken, steam tables. There should be a table somewhere. They ask you to fill that chart. Now I can find it. Just maybe that. Yes. Tutorial. This table 2 tutorial 1. I asked you to fill this and pass to me. This is very important. Okay.
Sir, we don't see the screen.
Oh. I'm very sorry. This one. Page, this is 1.10, page number 17. Page number 13. Yeah? Page number 13. Yeah? In the PDF document, page 17, but page number 13. There, this table. And this A, B, C, D, E, F plus the table. So I want you to do this. I didn't teach you this one, but you have to do this. You have to do this. That is very important. Okay? You have to do this. So why I should say you have to do this means, it is not necessary for me to teach you to do this for you. Okay? It is not necessary. Because my argument is at your ages, we need only to provide the directions. So actually today even discussions, those are directions. It's some special knowledge for you. Not time translating or preaching the book knowledge. The text is there for you and the paper based on the text. And even the entropy is there in the text, but I'm explaining that in practical ways, that's true, but you have to do this. You have to do this. And today I thought of discussing a bit about some practical sense relating to this, but today I feel it's enough and it's almost 2 hours now, reaching 2 hours. But you have to try this and you should send me by next Sunday, before next Sunday, because I need some CA assessments. So it is very important for you to send this thing. Earlier we have some assignments. That's true. Those are for your knowledge. You know, those are very special assignments you passed in the Google Classroom, but these are also important. That's all. So you all have done this. So if anyone know they are not doing the assignment, please be mindful that you will not get the CA marks to sit for the exam. Yeah. So you have to do that assignment very well. That is not for me, but for you. So 1.10, if you do this, it is after doing this, it is very nice to discuss this for you to gain some very good knowledge. Okay, this is very simple. Yeah. This is very simple. I will discuss the practical aspects and all. But before that, please do this and send it to me. Okay, do separate individually. Don't copy. Copying is something. Yeah, you can share the solutions, but at least you should understand. Otherwise, it's a shame, you know. It's a shame. So spend some time, put some effort, and do this one. So by next Friday, I should see you assigned. That is very important. Then only I discuss this. Tomorrow, sorry, next Saturday discussion should be based on this tutorial. There are a lot of things to discuss, not only this. There are a lot of things to discuss. So let me continue this step by step in the coming sessions. So very important, and thank you for listening. Your attention seems good. That's why you are gaining and you are really asking sometimes the question. So as working students, you know how important the practical sense of this. So you are okay. I feel you are doing very well. And also you can put some ideas. You can share the ideas with the class as well. Okay, that is very important. So do you need today this session, the notes? I can email you right now. You need this. Let me email this.
Yes, sir, we need.
You need it. So, go to my mailbox. I'm going to add this to intro before the list. As to be to today's 15 minutes. If I do PDF, it's easy for you.
Sir, we have another lecture at 3:30.
Okay, yeah, give me your email address. manufacturing, U or VT, how the email address starts with that. Can you tell me the mechatronics and manufacturing? 201, yeah, 2019, UOVT and B2, that is okay. The mechatronics one is, what's the mechatronics email address for that? Can you just tell me that UOVT? Mech 19? Tell me the mechatronics address. Someone, mechatronics student. Then if you are not telling the mechatronics address, I will send this to manufacturing. Yeah, tell me the address. Yeah,
Oh, sir, I'm mechatronics, sir.
sorry. Yeah, what is the mechatronics address?
Next lecture, sir.
Yeah, mechatronics email address.
Sir, I'll send you, sir.
Okay, I have this somewhere. Not yet. You're sending on the chat or the phone. Let me look for it. US BTech Mech 90.
Yes, sir. I send you, sir. To mobile, sir.
Yeah, okay, I got it. Thank you. So, okay, but I sent. Yeah, you will receive it. So I'm going to stop the class now. Thank you for joining the class and good luck to you all. So see you next week. Okay? Thank you very much for joining the class.
Thank you, sir.
Okay, bye.